Good morning.
I've already been.
If you want to go again,
I signed up to go to the cook and
it's like the happiest places on earth. The top 5 happiest countries in the world.
my sister already signed up for the trip. I said we're doing a group. Like I kind of the graduation, but Miss Absher did it's really that important.
But I mean,
It may not be what she.
He's like, you're only gonna be able to do these once. Just go do it.
well, I don't know. You'll get a chance to go in a 4-year school too.
And I want to be a pilot when I grow up so I can travel all the time.
Depending on what college you go to, there's always a study abroad program.
Well, I'm going to NC State for engineering, and even though I came here, it looks like I'm still going to have a really full schedule, so I'm worried that I might not be able to have time or the emotional capacity to go anywhere.
So you definitely need Calc 1. I mean, you want to start at Calc 3 and at NC State.
That's why I hope I pass this class.
Are we going to have Calc 2 next semester? Is it in the same way or is it different?
Same instructor, same book. We're thinking it might be in the afternoon.
Yes. I'm good with that.
I'm
not a
with
morning
these 8
person.
a.m. classes. Like, I don't like mornings, but
No, we're thinking it might have to be at 2 o'clock.
I could do that.
are there certain classes that you have to, aren't there certain classes that you have to take to go on this?
Yeah, as long as they're globalized. So Miss Johnson's American Lit class is globalized. Spanish is inherently global.
Do you have Miss Walters for public speaking?
I think Bert might have globalized chemistry.
British literature is globalized, right?
I don't think so. But you'll have American Lit too.
Wait, Bertha with Miss Johnson?
Yeah.
I think she told us it was because when I was in it, she was in the process of getting it globalized. And that's
I
why
don't think she ever did though.
She didn't?
Sydney, if you're interested in Ireland, I have a handout. Would you like it?
Do you have to take
You and Tori could go together.
Doesn't the humanities class
You could
for the
apply for a
Ireland trip,
scholarship.
isn't that globalized too?
What is?
The humanities movie part?
Well, that's kind of like the prep course.
So do you have to take the classes before you go to Ireland, or is it?
Just before you graduate. But, I mean, really, you don't even have to take any classes to go to Ireland.
You just
The classes are for the Global Scholars Program.
Oh.
In the humanities 180 class.
But, I mean, if you go to Ireland, you might as well be a global scholar, because that's really the big stepping stone.
The scariest part was the capstone. Once it's over, it's over,
What?
and it's not for good.
And I'm making it different. I'm revising the whole cap process. I'm creating a template so that students can do an e-portfolio using a website, and then they present their e-portfolio during the presentation, which I think will make it more streamlined and a little bit easier for the students if I just give them a template and say, fill in this template and then present it. I mean, it'd be much easier. Who do you present it to?
See,
Whoever comes, faculty, students, community.
when I presented my
You
capstone,
want an Ireland handout?
Miss Susan Venture, she said to keep it around 5 to 10 minutes instead of the 10 to 15.
You could apply for a scholarship.
So I did that. I made it 7 minutes, but I guess the other people who were like watching it and writing the notes, they didn't know that, so all of them put too short. I was like, she said that between 5 and 10 minutes. I did 7. That's like perfect.
Yeah, I'm working on a grant right now to help me fund changing all of this around, to fund the website creator and stuff that I'm working with.
So are you now in charge of like all the?
Global scholars.
Yep, you are.
And are you there?
I am. Can you hear us?
Yeah. I was suggesting you turn your camera a little bit. It's kind of only at one
Sure.
wall, so you can see people at the right end of the.
Ah, too far.
A bit more.
Hers says that too. One more, tick more.
One more.
One more.
I'm getting there.
See, Kyle and
A little more. We'll get to the top front chair.
one of the phrases doesn't still hand.
What, nothing missing here.
Oh, yeah, Emily, at the end, we wouldn't be able to see Ellen. That's good. One more. Oh,
Well,
How's that?
good.
that's pretty good.
Do you want me to move it a little bit more, or is that good?
Maybe one more.
Yeah, one more.
I think
I think that's good right
yeah,
there.
that way we can see close.
Yeah.
One of these ways. You gotta sit there. Can't see you there.
Want to go to Ireland with me? With me? Or you?
Oh, nice new books.
I have a smelly book. It smells like BO.
I think everybody has a textbook now, Dale.
Well, that's fantastic.
Finally.
Just click on
Finally.
your cup.
That's good. How were you doing it before? I mean, don't say it out loud. Were you providing materials of some fashion?
I was providing copies.
Great C word.
Now we're our pre-calculus class. We in our textbook we have a single textbook for pre-calculus algebra and trig, like most schools do. But then we added math 001 and we do it a little differently. So we use this textbook and split it up into 3 sub-textbooks. One for Math 101, one for Math 171, and one for Math 172. Which is nice, so if a student doesn't take 172, they don't have to buy that big pre-calc book. But, of publisher didn't get us enough books this time, so of the custom books, so students have been out of for the first week providing materials of some sort to them. But now we can't do that anymore, so they have to go buy a book for 1 month.
We're doing 0.5 of chapter 1.
Helen, you totally need legs. We need another motion to go.
You know, if I get to go for free, I'll
What's
go
a rough
for it.
time estimate of when
Sure.
we would get our grades back? I know like two of the factors are getting some new grades.
He has them.
You know,
He got them yesterday morning.
I don't fact, I study.
Oh, okay, that was. What year do you think it is, Sammy?
Oh yeah, just playing use a fax
I
machine.
don't even know how to use a fax machine.
Don't lie. Even I can figure that out.
You can still fax papers.
Figure it out. You just put in the number. And then you just
If I was giving unlimited permission to fax people, then
So I take it these 3 aren't showing up?
Did you get it?
Pretty bad.
Jenny said,
Jenny has signed a
I just
paper
faxed
saying
my
she's
neighbors
interested.
random things, and they
Jenny
went
and
down
Skylar.
well, I know, and I don't know where she thinks she's gonna get the
I
money
know.
for it from. That's exactly what I
I
told her.
told her to fill out a scholarship.
Yeah.
Oh, is math
Jill
club
is
meeting
not gonna
today?
pay for it.
Friday, 10 o'clock.
Jill is wrong.
Friday, 10 o'clock.
Yeah. But Jenny said that,
Yeah.
you and Miss Johnson were talking about her,
So
and then
we
she
need
didn't
to
know who
talk
Miss
to,
Johnson
like,
was.
principal or whatever.
I was like, Jenny, that's your
When's math club?
Friday at 10 a.m.
So that is a valid excuse to get out of high school?
Yes.
You can use that as an excuse.
What's that?
I say yes. Tell Miles you have to go to math club because it's the first meeting.
Because the only
Wait, what's
thing
on
that
Friday?
I is picture day.
Oh,
That's like a mandate.
Come to math club.
Miss Klinger.
Tell her Miss Klinger said you had to be there. Because we are getting free t-shirts.
Oh.
We just have to design them. But BFD's Wear Next Door donated
No,
us
hold on, I
t-shirts.
mean,
I didn't understand what the questions were.
I'm sure someone's happy, you know.
If they're that smart, they're not competing cheating.
Yeah. I'm sorry.
I don't know how to alleviate that because I can't be here until 6 o'clock in the week.
Read the whole question out, it's like, oh, question why?
We will keep you updated. We'll put it all in the Google Drive and you'll be able to see it.
You know who's great at the test? Probably not, right?
This your network's still down. I can't get on.
It's like, it's all freezing gross.
Hold on, what's,
I mean, but I have this hog and it's hot to
how did you, Jacob to, he was up here and Jamie flagged it down, like he did something on Jamie.
I do like them.
Wait, are we doing pictures?
I don't care.
Yeah.
I guess we're ready to start, we're missing.
Yeah, you're right. Are we doing the normal
Three
picture?
and family. Let's go ahead and get started. I did not get your tests completely graded. I made an effort so I couldn't do it anymore. And I don't have any one person's graded either, so don't say, hey, grade mine. I grade them, the way I grade tests is a page at a time. So I grade all of the first page for everyone and attempt to try to keep the grading somewhat uniform, especially on page 1, which was all explanation. So in that case, I actually did each problem. So I did 1A for everyone, and 1B for everyone. But it took a while to do that. In an attempt to try to keep grading uniform. Call it normed and so I'll try, I can't promise, but I will really try to get back to you tomorrow. The worst case is that Mondays. No, not Monday. Monday's holiday, so we have to do. Okay, but I'll really give it, I think I can hopefully get it done by, now the rest of it is easier because it's mostly it's either right or wrong. Your numbers and stuff either right or wrong. So rating the explanation is more very. Okay, so we're going to start on section 0.5 today, which is the last section of chapter 0, and is a prologue to what's coming in calculus. If anybody took time to include section 0.5, you want to assign the problem, you want to assign the reading. If you did, that's fantastic that you read through it. But the book does a good job, in my opinion, of describing that math in general is like building a skyscraper. You lay a good foundation with some basic definitions, and then from there you build layer upon layer, more theorems, build up from theorems until you get the whole thing. And so knowing and understanding how theorems work and how to prove them is important, because that's how you build a system called mathematics. That system of mathematics is important because you can use mathematics to solve problems, but also because the logical and critical thinking that goes into mathematics is important, even if you're not going to apply the math you learn to a specific problem. Just being able to think logically. Oftentimes, like if you think of a lawyer or somebody, they don't apply calculus, but the thinking of logical thinking involved in building a mathematical structure is actually very important to legal law. Oftentimes you see lawyers who had a great deal of calculus, math, simply because of that type of logic. That's why it's all important in that regard. So this section on 0.5 is on logical mathematical thinking, simple proofs, and understanding what that's about. So we start with, and so now we're going to, today, since we're starting with what I would consider new material for most students, although some of it is familiar, we will actually kind of introduce the material rather than just say, go on and read it. So we're going to start by introducing some stuff, some of which we're familiar, some of not. And as a study guide, I'll write some notes, but also as a study guide, your book has information. So I ask that you have your book open so I can say, look at this, and we can talk about it, so I don't have to write every single thing down, and then write down as we need. So with me on page 63, if you would just look at the definitions in the middle of the page. These are some sets that they're going to use this information to present the ideas. We're not, in this section, we're not going to develop calculus. We're going to learn about simple proofs and how proofs work so that we can go on to develop calculus. So our focus today is on some very simple concepts in order to get the idea of logical thinking. And so the simple concepts that are going to be used are on page 63, such as an integer. Everyone knows what an integer is, right? You should know what an integer is. Integers are whole numbers that are positive or negative, including 0. We have an assumption about integers that's implied that we will use. Can you write that one down? I'll start with here. So, So I wrote on the board, and I hope everyone can see that there. Integers are closed under plus, minus, and times. What does that mean? Well, that's actually a word from what would be called a advanced math class. So we're not going to get too in depth by that. But what we're going to understand is that if you add two integers, you get an integer. If you subtract two integers, you get an integer. If you multiply two integers, you get an integer. So therefore, I asked the question, are integers closed under division? I didn't write it down, so hopefully not. But why is it not closed under division? Can you give me an example of why integers are not closed under division? Yes. For example, integer 1 and integer 2 are both integers, but if you divide them, especially if you 1 divided by 2, you don't get an integer. Okay, So that's something that's kind of implied in this. We'll use that knowledge. Okay, other things. An integer n is divisible by an integer m if we can write n is equal to k times m for some k. So that's basically talking about multiplicity. So multiples of 4, what can be written as 4 times k or some integer k. Does that make sense? For example, 24. Everyone knows 24 is a multiple of 4. What would k have to be to show that 24 is in fact a multiple of 4? 6. Negative 20 is a multiple of 4. What integer do you need to use to show what k value you need to use to show that 20, negative 20 is a multiple of 4? Negative 5. That's all this is saying. It's a fairly simple concept, but you need to be aware of it. The next two are related to that. An even integer can be written as n equals 2 times k. Does that make sense from what we just discussed? So all even integers are multiples of 2. It's all that says. That seems obvious. And then the next statement ought to easily come from that. So if even integers can be written as 2 times k, then odd integers, which are the next one up from every integer, is just 2k plus 1. You see this? You need to realize that. By the way, that concept of, let me just take a moment, that concept of the next one up does not only apply to even and odd. It's easy for even and odd because you only have 2 cases. It's either even or it's odd. So it's 2k or it's 2k plus 1. But what about multiples of 3 or 4? Think about that. Like, for example, 3 is a multiple of 3. So let me just, for a side note, this is a little extension beyond what they've got. So now I'm going to talk about multiples of 3. This is some multiples of 3.
3, 6, 9,
6, 9. This is easy, right? You've done this since 2nd grade. But now, how many integers are there between each multiple of 3? 2 of them, right? Like a 4 and a 5 here. And then there's a 7 and an 8. Compared to, let's back up again, multiples of 2 were 2, 4, 6, 8, and the only thing in between them, and I guess I should be using a different color for that idea. Grab it a moment. Something like that. So in between the 2s and the 4s, there's a 3, and then there's a 5, and then there's a 7. So it's just every other one. But in multiples of 3, there's a 4 to 5, and there's a 7 and an 8, and a 10 and an 11. Well, so on multiples of 2, you've got the multiples of 2 are 2 times k, and the not multiples of 2 that land between them are simply 2 times k plus 1. We just went over that. This is an extension. The multiples of 3, how can you write the multiples of 3? Multiples of 3. 3k, yes. Multiples of 3 are 3k. Well, now, there is a problem. How do I write the not multiples of 3? The red ones. Question, Davidson? Like, how would you write a 4 in comparison to 3? Like, this 3 was 1 more than that 2. That 5 is 1 more than that 4. That 7 is 1 more than that 6. That's what this says.
You want
How do I
3K
write
plus
this?
1? Is that what you're asking for? You want 3K plus 1?
Yes, 3K plus 1 handle not all of the red ones though. It will only handle the first red one in each pair. So I'm going to get another color. The 3K plus 1 handled the 4. That's 1 more than 3. The 7 is 1 more than 6. The 10 is 1 more than 9. But what about that 5 right there?
You need 3K plus 2.
There you go. That has to be 3K plus 2. Or, that's right, this is 2 more than that one. But if you squint real hard, it also could be written as 3K minus 1.
Cool.
If I go to 6 and back up 1 on here, if I go to 9 and back up 1 on here, if I go to 12 and back up 1 on here, that same thinking can be applied to any multiples. If you apply multiples of 4, guess how many numbers are between multiples of 4? Yeah. So you could do 4K plus 1, 4K plus 2, 4K plus 3, or you could do some minuses in there and really make sense. Anyways, that's a little beyond. Let's just keep going. A rational number. It says in here, a rational number is a number that can be written in the form P over Q. For some integers P and Q, where Q is not 0. Questions on that? That's a definition you saw in pre-calc. Questions on rational. That's just setting the stage. Now we're going to get into what are called quantifiers. The for all and the there exists. Here's some of those. So a statement like this, for all x, p of x, is called a for all statement. So we call this a for all. The idea of for all is that every single possible x has to be true for this statement to be true. So here's an example. All cloudy days are rainy. Is that a true statement?
No.
Because I can find a cloudy day, like for us here, I don't know about Davidson, but for us here it's cloudy, but it's not raining right now. So this statement is actually false because I can find what's called a counterexample. And it only takes one. It only takes one counterexample to show false. The only way it can be true is for every single possible x. These are called quantifiers. I'll back up. The heading for what we're talking about are called quantifiers. And we have two main quantifiers. One is that for everything. The other one is that there are some. So there's kind of two ways to write that. We can say there exists is a kind of standard. Another way of writing it for some x. Those two are called the existential. This is the everything. Existential means there's at least one. So when you see there exists, or you see for some, that means at least one. So if you can find one case or more that satisfies this statement called P, if you can find one case, then that's a true statement. What does it take for this to be false? This existential statement to be false. So to be true, you just got to find one. To be false, what has to happen?
It never happens.
One of them has to be false to be false. So there's two different things here. To be true on the plural, all have to be true. To be false only requires one. But there exists, to be true only takes one. To be false requires everything to be false. Let's see. How can I come up with I was going to try to use rainy again, but there exists. Now let's use some. I want to back up and start over. So, on rainy days, have no clouds. So here I'm trying to write something to cover myself a little bit. Has anybody seen it rain with the sun still shining because the clouds are kind of over here and the rain's kind of blowing down, hitting you, but you still get sunshine? Well, I'm taking out that case by saying no clouds anywhere. So no clouds anywhere. That's not possible. You gotta have clouds that rain somewhere. So that one is false because everything possible is false. So I only needed one to say that if I could have one day when there's no clouds anywhere, it has rain, that would make it true. But I don't, so this is false because I cannot find any rainy days without clouds. Okay, so those are the two types of quantifiers. One more time, for all has to be true, has to have every single possible case true, but to be false only requires one bad apple, and it's false. A existential that exists only requires one to be true, but it requires everything to be false in order for not be true, be a false statement. Questions on that? Look at some examples with numbers instead of doing rainy days and clouds. Rainy days and Sundays, or Mondays. All right, guys, distracted back. For example, consider the problem on page 64 now. Let's look at these quantified statements and decide if it's true or false. On the top of page 64, for all real numbers x times x plus 2 is equal to 2 times parentheses x plus 1. That's true or false? It's true. Why is it true? Because you can't find an x, you cannot name for me an x value that doesn't satisfy that. Any x you plug in is going to be true. What about the next one? All integers, x, all integers x, 1 over x is a rational number. Someone in Davidson, what do you think? I just got an answer for the first one. I want a second one. On page 64. All integers x, 1 over x is irrational. Sammy's got her hand up. What do you think, Sammy?
You can't put 0 in place of x there because it would be undefined.
Correct. So the statement is therefore false because you can find at least one value somewhere. You can find at least one value that makes it not true, so the whole thing is false. That's good. Good, good. So next one, there exists an integer x such that x is even. I see nod yes. Davidson, do y'all agree that's true?
Yeah.
Yeah.
Okay, why?
Because there only has to
2 is
be,
even.
yeah, there only has to be one.
Yes, there exists means you only got to show me one case. 2 is a perfectly good example. So there is an integer x, we'll call it 2 if you want, is even. There's actually lots of them, but you only have to show me one. There exists, in the fourth case, there exists a real number x such that 1 over x is equal to 0.
That's false.
That's false because why? Because you can't name for me an x value that will divide into 1 and make an answer of 0. Now, we might, later in calculus, discuss the idea of division by infinity. 1 divided by infinity actually comes out to 0. But that's asymptotic behavior. We'll get to that later. But for a fixed number x, there isn't one. You would have to use some kind of limit for limits here. So that would be. I'm not talking limits, we're talking an exact value. Okay, next up. Consider mixing 2 quantifiers together. And this is what we're going to see when we go into the next chapter. We're going to see a mixture of 2 quantifiers, and that gets a little confusing. So right in the middle of page 64, there's 2 statements, and let's look at those closely and make sure we understand what they're saying to us. Statement 1, right in the middle. For all x greater than 0, there exists a y greater than 0, such that y is greater than x. I think I'm going to, my black pen and write that down. Okay, so I'm going to go to this page. Let's write that down. For all x, there exists y, such that y greater than x. All x greater than 0, there exists y greater than 0, such that what, y is greater than x? All right. What's this? Yes. Okay. So there's our statement. It's in the book. I've written up here so we can talk about it a little bit. Okay, so what does it mean by this for all right here? What's that telling you?
That is.
Read the sentence left right. So you have to, this statement has to be true. Has to be true. If it's going to be true, so if the overall statement is true, then it must be true for every single possible x value that's greater than 0. So must be true for every possible x that is positive. If we got a greater than 0, okay? So now what is this? There exists y greater than 0. What does that say to you? I just have to be able to find one y. It doesn't have to be all y's, but just find one. I have to be able to find must be true for at least one y positive. So one positive, I gotta be able to find one positive y that makes the statement true. So now let's look at the conclusion. This is like a piece de resistance. This is the end. Okay, so what does it say? Y is greater than x. What do y'all think about that?
X, that is y.
Positive?
Is it possible, if I pull any x out of my hat, I'm imagining an x value in my head right now. I'm not going to tell you what it is. So, because it has to be true for any x. So if I'm imagining a particular x, I'm not telling you. Can you now find a y value? Just one, just got to name one. Can you find one y value out there somewhere so that the y is bigger than my x? Can you do that?
Yes.
Jacob says yes. Jacob, how would you identify that?
I'll say if you suppose two, for example, 4,
Yeah, we'll make it even simpler. The number I'm thinking about for x, I'm going to let my x equal m. I just got some number in my mind. Now, can you name for me a y value? So this is my mind number, right? My games. Can you name for me a y value? Jacob said, yeah. If it was 2 for x, I could pick y. Y is 4. You're right. But now, can you? But that's only one example. I have to do it for every example, and I don't have time in this world to look at every single possible x value and say, yeah, I can find that. So I'm going to do it for the number m. Can you name a y value that you know is going to be bigger than x, no matter what this n value is here? Choose m plus 1, sure.
Oh.
Shut up.
So then, clearly, m plus 1 is greater than m. So y is greater than x. Yep, so that's a true statement, because no matter what n value I happen to be thinking of, I can pick one bigger than it. That's easy. Now let's go to the second statement. What does the second statement say? I'm going to go to the left. This is harder. Read the second statement to me, please, someone loud enough for everyone to hear.
It says
How about Joe? I'm volunteer Joe. Everyone's looking at each other like, who's it? Who's on first? What's on second?
there exists y greater than 0 such that
Wait, slow down. There exists y greater than 0 such that
for all x greater than 0,
for all x greater than 0,
y is greater than x.
y is greater than x. Okay, let's take this one apart bit by bit. So it starts off with there exists y greater than 0. So what does that mean to you? About 3. Bree's here, right? Or is that Emily?
No, that's Emily.
Or Emily moved over, so Bree's not here.
It's Chrissy.
Okay. It's hard to see faces on the camera, on the TV. Okay, so Emily, help us out. What does that mean?
That means that only one of them has to be true. Only one thing of that has to be true?
Correct. So we need at least one y value that's positive. Okay, so we need that. In order for the whole statement to be true, we just need to be able to find this one. Okay, good. What does all x greater than 0? Justin, what's that mean? What does the for all x greater than 0 mean?
That all now by x.
So I have to make it true for every single possible x. For every possible x that's positive, this has to be true. So I have to be able to find one y where no matter what x value I pick, this statement has to be true. And then it has to make y greater than x. So before we answer the question, I want you to just make sure, look at the first, compare the two statements. They're on different boards now, so you can't. You look at your book. The first statement said for all x greater than 0, there exists y greater than 0, and then blah, blah, blah. This one says there exists y greater than 0 such that for all x greater than 0. So do you recognize that the two quantifiers are just reversed? That's going to make a difference. So think about this. Can you identify for me a single y value, just at least one y value, such that no matter what x value I have in my mind, y is going to be bigger than that x?
Does infinity count, or is that cheating?
I can't hear you, I'm sorry.
Does infinity count, or is that cheating?
That's the whole gist of the problem. Infinity is not a real number, it's a concept. But because the real numbers are infinite, then this in fact is false.
Okay.
Right? Because as a counterexample, this is saying I can, in words, this is saying I can find a biggest real number. If y is always bigger than every single x, then there's a biggest real number. But there's no such thing, or as it just said, real numbers are infinite. So this is false. As a counterexample, I would kind of do the same type of thing. So I would show it's false by giving a counterexample. So one way to show it's false is what we call a contradiction. So let's assume that there is some y value that's the biggest. You know, let's assume y equals m satisfies statement. So let's pretend we're gonna show a contradiction. If we get a contradiction, then we know it's false. So pretend for a moment that there is some biggest number. Well, if that's true, then this has to be bigger than every possible x out there. Is it true? Well, can you identify an x? Can you give me a counterexample? Can you identify an x that's not smaller than this?
X plus 1. No, m plus 1.
This says y has to be bigger than x. Well, that means x is smaller than y. Can you give me an x value that's not smaller than m?
M plus 1.
I heard someone speak up again, please, Davidson.
M plus 1.
How about m plus 1? Sure.
I don't buy it. He said that's the biggest possible.
And x equals m plus 1.
Hypothetical to begin
It
with.
has to be every possible x.
Been on a
X equals m plus 1. We get y greater than x gives us, if I'm assuming the statement is true, then this has to be true, but if that's true, then that gives us that m is greater than m plus 1.
That's wrong.
And it's false because why? What if I subtract m from both sides?
Then you have 0 is greater than 1.
0 is greater than 1. You know from first grade that that's not true. This is false. Since that's false, then the statement could not have been true. So I've shown it's not true by providing a counterexample. But the counterexample is a little bit harder. I can't just name a singular number like 7. I have to be able to say that this isn't going to work with any of this. Okay. Enough of that. Next up is implications. I'm still on page 64. Implications are the standard way that theorems are written in math. You've seen them as if-then. If-then is called an implication.
I feel like asking a question.
Implications. way, before I start this, I just had a thought. My brain went on a little tangent. I'm sorry. Can you go back to this book for a minute? So this, in math, we oftentimes write symbols to represent words. Like instead of writing out the words greater than, we put that symbol there, etc. Well, it turns out, and you don't have to know this for the test, but I'm just going to tell you anyways. Those words right there can be symbolized by a backwards capital E.
Is that epsilon?
Words for all can be symbolized by an upside down capital A. And in fact, these words right here can be symbolized by the backwards curly E that you saw a member of. We saw that a member of a set. If you turn that backwards, you get such that. That's just a conventional mathematics symbols. So you can write all of this very concisely without a whole lot of ink on the paper by using these symbols.
Joe, can you move that up just a tad so they can see it?
Yeah. Can you move up a little bit, Joe? There you go. Can y'all see now?
Yeah.
Or
That's good.
That's good.
Rezo has a question.
question, Reza. I'm sorry.
I have a clarification question.
Okay.
So to disprove there exists statement, you need to provide a counterexample, or not a there exists statement, a for all statement. You just need to show one instance where it doesn't work, right?
Correct.
So, but you said it's not okay to use a numerical example, so I couldn't do, like, use actual numbers, like 1 and 2 or something.
Well, okay, for all, if it starts out with a for all, that's one thing. But this starts off with a there exists. So in order to show a there, so ultimately the first quantifier is the overall control. So over there, the first statement, the overall control was a for all. So if it was false, I just had to find one that didn't work. If this one's an overall there exists, to be false, it means there can't be anything that exists. So I can't literally look at every single object and say, this one doesn't work, this one doesn't work, this one, I have to do it more in theory with a variable. Does that make sense now?
Okay.
Answer your question.
Yes.
So back to regular schedule programming, we were on implications. So I'm at Bill Board again. Implications. These are typically what we would call if, ... then, ... Those types of statements are called implications. In symbols, this first statement right here that comes after the if, we might call that A, and then the then, the if-then kind of go together and give us this arrow symbol, and then we'd have B. So if A, then B. But we read this symbol as A implies B. So that symbol you read as implies. So what about this if-then statement? So here's an example. If it rains Friday evening, then I will stay home to
That's a good qualifier for me.
What about true and falseness of this statement? We've been talking about true and false. What makes it true? What makes it false? What would make it false? There's only one thing in the world that can make it a false statement. Everything else is true. So listen to the possibilities. So What if it rains Friday evening, and then you do stay home and do homework? Is that true?
Yes.
That would be true. What if it doesn't rain Friday evening, and you don't stay home and do homework? It's still true. What if it doesn't rain Friday evening, but you do stay home and do homework? That's actually still true, because the reason it's true is it's not false. The only case that's false is if it rains on Friday evening and you don't stay home and do homework, then that's a false statement. That's the only case that it's false. So anything else has got to be true because that's the only case where it's false. So it's only false in, I'm going to use some words and I'll come back and identify those. When the hypothesis is true, but conclusion is false. So the overall implication statement, overall implication, has a true or false sense to it. And that only is false. That overall if-then statement is false only when the hypothesis is true and the conclusion is false. And which one's which? So going back over to the symbols, the A is colored for hypothesis. Well, hypo means below, and thesis is, well, that's like a thesis. Propositioning a theorem, so below a theorem. And then your conclusion is the B. It's called the conclusion. And up here, my statement that is the hypothesis is raining on Friday evening. And my conclusion to this is that I will stay home and do homework. Okay, so that's an if-then statement. Only is false when the hypothesis, the first part, is true with the second part false. Other things related to an implication statement is the converse.
That's a shoe.
So converse is statement in symbols. B implies A.
Oh, dang.
So how would you think about symbols and words up here? Could you rewrite my implication as its converse based on what we just discussed?
If I'm staying home to do my homework, and it's raining,
Exactly. Y'all, Davidson, y'all have a suggestion? Joe said it. Do y'all have a suggestion? Did you hear Joe?
We got that if I stay home and do homework, then it's raining on Friday night.
Yes, that's exactly correct. So if I stayed home to do homework, then it's raining on Friday night. Now, is that the same truthness as the original implication? Does that statement have the same truthness?
Sure.
No.
It's saying that if you do the homework, then it's gonna rain automatically.
Because
No.
if I stay home and do homework, then it rained. It's only false when I did homework, but it didn't rain.
Yeah.
But in the other direction, if it rained, then I did homework, that same comparison doesn't, y'all with me? Okay.
It's a
This one is false. This one's false here. If you had a true rain and a false homework. So that statement now becomes false. If you switch it around to the converse, you're saying, if I stay home, do homework, then it rains Friday evening. The only way that's false is if you have a true here and a false there. Y'all with me without writing all that out? But having a true on the I will stay home and a false on the it rained Friday evening, on the original implication, if this is false and that's true, the overall implication is not false. So therefore it's true. So my point is, what makes the converse false does not make the original implication false. Therefore they're not equivalent. Although that is a misperception by many people. So I'm trying to get you to say, no, they're not equivalent. So if I write a statement and I write it the wrong direction, it's not correct. And in fact, some of you did that on the test. Okay, so one of the problems involved horizontal line tests. Horizontal line test. Horizontal line is looking for one-to-one function. That question on the one-to-one function, remember that? Okay, so first of all, a function is a relation where every x value matches with only one y value. That's a function. A one-to-one function is a function where each y value matches to only one x. That's different. Many people wrote a one-to-one function is a function where each x value matches to a unique y value. That's the wrong direction. That's still the definition of function. So many of us wrote what we thought was the definition of one-to-one, and it was really still the definition of just a function. So you had your order of your implication wrong. Other statement that is related is called the contrapositive. 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 So contrapositive would be something like, if we use purely symbols, the symbols typically used are something like a squiggle, it's called a tilde. Tilde B implies tilde A. But now the tilde there, that means, or is interpreted as, we don't read it as tilde, we read this symbol as not. So it's kind of like a negative sign on a number, except for it's not a number necessarily, so we don't say negative. We don't say negative B. It's the opposite of B, so it's like having negative, but we read it as not. So let's go over here. Can we state the contrapositive of this statement? This time I should write it out. Can someone give us a contrapositive? How about Kyle? Can you give me the not B implies not A of this statement?
Well, can you explain what a contrapositive is first? Because I'm not clear on the definition of it.
I'm sorry, I couldn't hear you.
Can you explain what a contrapositive is? Because I'm not clear on what the definition is.
Okay. A contrapositive is an implication, so it has to have an if and a then. So that tells me I gotta have an if and a then. And this symbol means not. So you're doing the opposite of whatever this statement is.
Oh, okay. So if it does not rain Friday, then I will not do my homework.
That is close to being correct. You did the nots correctly, but we want the B first and the A second. So
if I do not stay home and do my homework, it will not rain. I'm an idiot.
So what do you think about that statement in terms of its truthfulness in relation to the original implication? You know, I started with one original. Well, I didn't write it, but we talked about a converse implication, and we decided that it wasn't the same. But the contrapositive of the original implication, is it the same or not the same as the original implication in terms of its truthfulness? Is it true at the same time? When real events are happening, is it representing the same thing? And Maddie says yes. In fact, it is. So this should have been, I apologize, I left out off an if. If I did not stay home to do homework, then it did not rain. Because of the negations in there, put those knots in there, it gets a little bit squidgy in my mind. So I'm going to help you see it, I'm going to tie the if-then idea to one more thing. Y'all remember Venn diagrams?
Venn diagram?
Venn diagram.
Venn.
You got 2 circles? Okay. Well,
Yo, I remember Ben. He was real. I mean, I feel like this is more intense than a Venn diagram. Because you're talking about like an independent event. You're talking about like B being predicated by A, and talking about it vice versa as well.
Oh, it's just.
certainly you've heard of and seen a Venn diagram before. Normally you see it looking like this.
That's a rectangle? Okay, okay.
That was already confused.
Justin, I'm sorry, what was it? What was it?
You just drew the rectangle and
Rezo was
Rezo
confused
had-
because he thought you were gonna make
Just
a
a
Venn
rectangle.
diagram.
Oh, yeah. A Venn diagram usually involves sets, and set A is represented by a circle, and set B is represented by a circle, and the rectangle represents the universe of everything.
Oh, okay. I get it.
This part would be the intersection of the 2 sets, and so on. You've seen that. Well, now let me change my Venn diagram somewhat. So that's what you usually see.
I seen this.
Let's try another one.
We about to evolve. We about to get geeked. Oh
I'm
yeah.
going to change colors now. Make it
Oh
more-
yeah. This is what I live for.
I found it like first.
Oh sweet. Is it gonna get bigger? Oh yeah. That's it.
So this is a Venn diagram of the relationships of 2 sets A and B. And what would you describe the relationship of this to be?
To be.
Correct. All of A is in B, but not necessarily all of B is in A. That's exactly right. Well, this matches the idea of an implication. This is a picture of
Got him.
Can you see that if you are in set A, if you are inside set A, then you have to be also inside set B?
Mm-hmm.
That now helps you to see why the contrapositive is equivalent. What if I put not B implies not A? So is that equivalent now? So if you are not in B, then there's no chance at all that you're going to be in set A.
Yes.
Will be
Okay.
true at the same time. Okay. Already mentioned counterexamples previously, so on page 65 they talked about counterexamples. We did some already, so I think we're going to call that covered for now. Question? Do we have a question from Davidson? I'm sorry. I think Chloe stretched.
Okay.
That's a good idea. Let's stretch. It's 9 o'clock. Counterexamples to implications. page 66, we need to mention that. We sort of covered it, but let's just talk about it real quickly. Then maybe do another thing. On page 66 at the top, in order to show, I mean, I talked about it, but this is a theorem stating this is what you really got to do. In order to show that an implication is false, you have to show that there is an example X value where the hypothesis A is true, but then the conclusion B is false. So once again, we said this implication is false only when the hypothesis is true and the conclusion false. If that happens, that makes the overall thing, overall statement, overall implication false. So in order to show that, you have to give an example, well, one example where the hypothesis is true. Give me an example of rains on Friday, but I didn't stay home to homework. If you can give me one example of that, that implication is false. Okay? So that's how you counter example and implication. Give me an example where hypothesis is true, but the conclusion is false. Now, last thing is simple mathematical proofs. So we're going to demonstrate a simple. We've done a little bit already. We'll do another one that's maybe a little more formal. I'm going to go back over here to the left, I guess now. So when we're going to do a proof, so let's say the problem is something like this. This is kind of like the one in the book, I guess. Prove all multiples of 6 are even numbers. Just similar to the one above, not identical. So, do you see the all there? What does that mean?
Yeah, we just have to find one.
It's a big capital backwards E.
Actually, it's a capital upside down A.
Okay, I'm sorry. I don't
Again, you don't. Yes, not you. Anyways, what does it mean about proving it to be true?
We just have to find one to prove it wrong.
Every one of them has to be true. And to show it's false, you just have to give me one example. So, is it false or is it true? Well, it's true. So I can't prove it true by giving one example. If I say, oh, look, 12 is a multiple of 6, and 12 is even. Therefore, this is true. No, you show me one example. That's not satisfactory. You've got to show me either you've got to take the rest of your life and look at every possible example out there, and then once you're done, which, by the way, is not possible. People are trying to do that with some other things, and you cannot enumerate all the possibilities. So what we do is, since it's a for all, and we want to show it's true, we've got to do it in general for any number that satisfies the condition. So we'll start this. Let X be a multiple of 6. So I'm going to prove the implication. This is kind of like an implication. I'm going to show that if I have a multiple of 6, so almost think of this like an if-then. So if multiple of 6, then even number. So I'm assuming the hypothesis. This is now my hypothesis. In red, I'm just putting notes in red. This is my hypothesis. Hypothesis
is assumed or assured.
You got two paths. If you're trying to prove true, then you have to show the conclusion is also true. If you're trying to prove false, then you have to show that you can find a conclusion that doesn't satisfy. I'm trying to prove truth, so I'm trying to make this happen. So now I got to use my knowledge, some algebra, and get there. So if x is a multiple of 6, what does that mean?
If it's X times 6.
This means
First page of this section, what does it mean?
6x or k6k. Whatever.
Yes, that means x equals 6k for some integer. Okay, that's exactly right. Good, Chris. But what do you know about the number 6?
It's even.
And think about, let me lead you a little more clearly. Think about the number 6. Think about the concept of evenness. What do you see between those two there? It has to have what? It has to have a multiple of 2 in it, right? Does 6 have a multiple of 2 in it? Yes.
Yeah.
So, since x equals 6k equals 2 times 3k.
That's good.
And 3k is an integer by closure. Remember that? Remember at the very start, closed. We talked about closed.
Yeah.
Because if I multiply an integer k by another integer 3, I get another integer. So that's an integer. And 3k is an integer. Then x is even.
Okay.
Because we've written x as 2 times an integer. So we've shown that it's even. So I've gotten to the conclusion. Every possible x value, I didn't say what x is, every possible x value can be written, if it's a multiple of 6, it can also be written as a multiple of 2, fairly easy. So therefore it's even. So that's a very simple, what we call a number theory proof. And you have a couple of those in your exercise to practice on. It's really simple. I guess we're about out of time, so for homework, oh gosh, let's say number 1, of course. And I'll try to remember to post this online as well. I didn't do that yet. And I think on the first group, you just have to identify. So let's try 17 through 46. But you're not really doing much except for kind of explaining. And then try a proof, those are just explaining. And then a proof, try proof number 76. See if you can do problem 76. What did I just say? 1, 6. Talk about that tomorrow, and then we'll see what happens next. So, I'll have a good day. It is 9, isn't it? It's 9. Oh, 9:08. Well, hey, you got more than you paid for today. You're welcome. I'll send you a bill in the mail. Thank you all. See you tomorrow. See you, Davidson.
Hey, Mom.
We're going on a trip on there.
When I saw one time.
Now,
That's what I was just telling Emily. I was like, well, like I actually, and I didn't want to do myself.
Are you guys feeling better?
Not really.
It clicks.
Not really.
I mean, you
You're
know, it
through
would be
your
nice.
pre-calc review.
I